there, and I went there. This is amazing. Again, I keep forgetting that this exists, and I want to show my pre-calc statistics here, but I don't know if you guys notice what's going on here. So what's happening is, as you move around, this tangent is going to become infinitely long, because it's going to have to go, it's got to be perpendicular to the circle, right? So as you move over, it's going to have to become longer and longer, and it kind of makes sense, because what's the tangent of 90 degrees? There it is, undefined, infinite. So it'll become infinitely long. So this is a really interesting picture, because this does kind of capture the idea of the tangent of the angle and the tangent line and how they are related, because that is tangent to that circle. Now secant's two different kind of definitions that are used at the same time. There's no real good connection between the secant line and the secant in trigonometry. Notice this too, this is kind of cool. Anybody can tell me what kind of triangle this is?
Equilateral.
What must the angle be here? 90. So it is a right triangle. This is the hypotenuse. Tangent squared plus 1 squared equals secant squared. Tangent squared plus 1 equals secant squared. Holy shit! That is the identity, if some of you remember. So this picture is kind of neat. You can see all the identities playing out. You can see the ideas and how they grow and shrink. You can see, look at all the co stuff is up there. Look at all the non-co stuff is down here. Interesting. All right, that's enough of that. I just wanted to show you that because somebody was asking me about the connection the other day, and I forgot to show this picture. All right, so the last little bit we'll do while you're in a good fried and upset state. My quizzes have a tendency to do that to people. What was it? Somebody had a question from 3-3?
37.
All right. It's kind of involved. Okay. All right. So we got a ladder up against the wall. The ladder starts to slip away from the wall. So this starts to slip down. Starts to slip away from the wall. How fast does x change with respect to theta?
Yeah. We are? I just kind of figure out what I'm taking the root.
This is 3-3 number 37. All right, now here's what's going to save your ass. Can you rewrite in symbols the question? What does it ask me to find in symbols? No. How fast x with respect to theta? How fast is x changing with respect to theta? So in order to find that, I have to find a function of what? I need to find something as a function of something. Say it again.
X as a function of theta.
You got it. Yes, I have no idea if you looked into that, but yes, I'll give you credit. You have to find x as a function of theta, right? Dy dx, what do you normally attack with? What would you have? You would have y equals a function of x. So if I want dx d theta, I have to first have x as a function of theta, and then I can take the derivative of that with respect to theta. So can you get the relationship between this and this? Of course you can. Just trig. In fact, that's coming from the trig section, kind of makes sense. So figure out what the trig function is that relates x and theta. You might have to bring 10, of course, in.
Would it be sine?
Yeah.
It is sine
Or
x.
Yeah, because you got sine. So sine, what is it with sine theta equals?
X over 10.
X over 10. So x is a function of theta, so just move the... Now you get x as a function of theta. Now I get dx d theta. Okay. So you guys can do that. It's all about changing the question into symbols, because then you can more directly say, what do I have to do calc-wise to make that happen? Yes?
Yeah.
Oh, all right. So in the reading and from before, we know that the limit as x goes to 0 of sine x over x is 1. Okay. So they will be able to actually prove that. But actually, everything we've known so far, even what the book has done, is just been feeling it out and looking to see what does it look like it's doing. So if we know this, now watch. So if I said, what's the limit as x goes to 0 of sine of 4x over x?
Well, you have to get 4.
It's not the right form, is it? What's missing?
4.
What piece is missing what exactly?
Go there on
The bottom is missing a 4. So this is interesting. This is going to become huge the second part of this class, or towards the end. If I do put 4 there, what did I just say? If I do put a 4 there, I can't just do that. How do I balance out what I just did? Yeah, I'll just put it out there instead. So overall, what did I just do? Nothing. But now this is sine of something divided by that same thing. Its limit is 1, so the limit of the original problem is actually 4. So if you look back, I think on one problem I had like tangent of 5x over 3, and the limit ended up being 5/3 or something. There was on the first quiz. It's related to this idea. So now the problem you're asking about is like sine of 4x over sine of 6x, right?
Yeah.
So what's sine of 4x missing underneath it?
6 over 4.
What does sine of 4x need underneath it? You guys just did it. And what does sine of 6x need above it?
6.
All right, 6x. All right. Work with that.
Wait, 6 or just 6x?
6x. Right? What does it say? Sine of something divided by that same thing. The limit as that thing goes to 0 is 1.
So we multiply from 6x.
So if I put a 4x here
and 6x.
and a 6x there, what do I really... The x's already take care of themselves, don't they? What do I have to put out front?
4x over 6x?
No. I wouldn't be able to either. I can't take an x out and but these x's already take care of each other. Oh, that's nice.
Yeah.
They take care of each other.
But then what's the point of the x being
To
there?
fulfill this, the limit's not 1 unless I have this complete.
So limit is 4.
So the limit of this is 1, the limit of this is 1. Yeah.
So look at these, you just 4
And then if you do enough of those kind of problems, you'll start to see the shortcuts.
Yeah.
But you can't see the shortcuts until you do some more problems. So that overall I didn't do anything to cancel back out? Yeah. Alright, so before I let you out, with my 2.5 minutes I got left, yeah, we're just going to do this little tiny thing. So let me see what you guys think of this. So I know if I have y equals, let's start it easy, 3x squared. dy dx would be what?
6x.
6x. This is amazing. So notice what happened. I'm doing with respect to x, so any y's don't become 1, right? It became dy dx. Yeah. So we're starting to look at this a little bit differently. What did I do to both sides? Took the derivative of both sides. I love it. So any x stuff, I don't have to put a d, because dx if I do chain rule, oh shit. What's inside is x. Well, dx is just 1, so that's why it doesn't normally show up, because it's just 1. Unless it's something more complicated inside, and then its derivative will show up. That's how we know so far. So I actually do chain rule always. It's just that most of the time it cancels. Who cares? So what I'm saying is this now. What if I had y squared equals 3x squared?
You get 2y dy dx 6x.
All right, let's slow down. Yeah. So if I want to take the derivative of y squared, isn't y is a function of x, isn't it? So this is chain rule. What's the derivative of something squared? 2 times that thing times the inside gets a term. Slow down a second. So every derivative we've done so far has actually followed that rule. They just all have been very simple. It's just y to the first power. So there's been nothing else. What is the derivative of y? 1 times the derivative of the inside function. So it's nothing really major going on there. But the minute I get both my y and my x are involved in functional kind of stuff, then I have to take the derivative correctly. So what I'm saying is, try to shove all this in. I want to get the idea out there. Where's that example I just said? Too bad, Jeff, you don't have it. No, it's not. If I have, let me see, help me out here. If I had 2x plus 5 to the 7th power, what is that derivative?
7, 2x plus 5,
minus 5, plus 5, so 6.
times 2.
I love it. So that was the derivative inside, right? So if I had y to the 7th somewhere, its derivative would have to be 7y to the 6th times
dy.
dy dx, for example, right? That doesn't seem crazy, right? Right. This is implicit differentiation. Why do we call it implicit? Because here, what's the function I'm dealing with? It's explicitly stated. Right? This is the non-National Geographic version. This is in your face. Here the thing is killing it. It's explicit. This is implicit. It's like, what is y? Oh shit, it's hidden. It's implicit. But I know that y is a function of x, so it has to be multiplied by its chain rule piece. It can't escape that.
So, what part would you multiply the 7y raised to the 6? Would you raise it, maybe multiply it by...
Well, so if that was in my prop, so if I had, for example, if I had x y to the 7th equals 2, and I want to take its derivative, I want to find what dy dx is. So what do I have to use here? Product rule. So what's the derivative of x
1.
times y to the 7th plus x times the derivative of y to the 7th would be
dy dx.
kick ass. That's the chain rule piece, right?
Equals 0.
Equals 0. Kick ass. And now, if I want to get dy dx, I just got to solve for dy dx.
Minus.
Alright, so you subtract, divide, well, let's crap, you get dy dx. So dy dx equals negative y7 over x7y6, and then you can cancel some y's out. Alright, so obviously, we'll do more of that.
Is that 3-5?
That's 3-5. I just wanted to step a little bit into it to show you what's coming. Oh, Haley? Are you out there? Haley? Tristan? You yet? So you should definitely be in the 3-3. If you're not in the 3-3 yet, you're behind.
So we need tomorrow, we're starting 3-4?
No. We just now talked about 3-5. 3-4 we're done with, but we finished it last time. It's the chain rule, so we're going to be fully into it next week. Yeah.
There's one more